Hey everyone, Mr. Tegmeyer here. This is part 3 of the material testing. And in part 1, we looked at tensile testing and what we can find with tensile testing. We found that we generated a graph of force and displacement. And then from that, in part 2, we looked at the stress-strain curve. So we took the force and the displacement. We manipulated that data a little bit to come up with something that is specific to a given material, and we found all kinds of cool information that we could gather from that. Now here's just some other a little bit of everything really that covers material testing. So we're going to look at hardness testing and some other things. So let's get started. So you remember in part 2 we left off with this slide. We looked at the stress strain curve and we talked about failure, and because that's what a tensile test is, we pull something apart until it fails. So what does that look like? What does an actual part look like? Well, here's some actual photographs, and what's different about these things is that here on the left side you can see some necking, as opposed to the right side, you see something that's pretty much, it almost looks like a clean break. And the major difference here is brittleness. Here I have on the left-hand side something that's pretty stretchy, if you will, and over on this side something that's a lot more brittle. This might be, I don't know what material it is, but it might be like a ceramic. And over on the left side, this is going to be a softer type material. And then, of course, there is everything in between. So as you can imagine, when you're doing a testing material, you might not know what the material is. That's one way to kind of tell how brittle something is just by looking at the cross section and looking at how it breaks. So if we took a look at the stress strain curves from the parts on the previous slide, if we looked at the part on the left, the stretchy one, if you will, it might look like this one here on the left, whereas the brittle one might look like the graph on the right. What's interesting to note, though, is that if you look at the ultimate strength or the tensile strength, they're the same. But what's very different is how much strain I got on the left part. It goes way out here as opposed to the brittle part, which is over here. So there's actually something that we can measure called brittleness, which is almost related to ductility. So it's not ductility, but it is, and it's not the lack of strength, but it's really kind of a measure of strain as well. But so if you see a stress strain curve that's pretty narrow, if you will, as opposed to something that has a lot of strain, that gives you an indication of how brittle something is. And we can actually put a number on that. We're not going to do that here, but I just wanted to expose you to that idea. Another cool thing we can get from the stress strain curve is something called toughness. And it's the area under the stress strain curve, and it's technically defined as the work per unit volume that's required to fracture the material. And we're not going to do any problems with this in class, but if we were to calculate it, you'd probably break this up into parts. You have a triangle, some sort of rectangle, and then some sort of semicircle or something like that where you would estimate the volumes. And that's what it is. It's an estimate. You can actually have, if you know what the curve here is, you could fit that mathematically and come up with a more exact number. But toughness is the work per unit volume. So we've talked up till now about tensile testing. And tensile testing, again, is where we pull things apart. But there's also something called compression testing. And if you stop and think about where that might apply, think of concrete. Concrete is probably the most common thing that we might test in compression because that's how it's designed. It's designed, you put concrete on roads and bridges and so on, and it's because of its great properties in compression. And the test is done in the same machine, for example, you see here the machine on the right, and you see the red rectangle here. And instead of pulling apart, you crush it. So you have a force going this way, and you have a normal force coming up this way, and you crush it. And what happens is, instead of the cross-sectional area getting smaller, it's going to get bigger. And again, you can measure failure and come up with some values there for how strong something is in compression. Finally, one of the last things to look at or to understand is something called hardness. And there are a couple of different kinds of hardness and a couple of different ways to test for it. So hardness basically is it's materials resistance to permanent deformation. So yes, you can look at a stress strain curve, but there's something called a Brunel hardness test and a Rockwell hardness test. They're kind of the same, but they use two different methods. So a Brunel hardness test uses a tungsten carbide ball, and you press for 500 pounds and 15 seconds, and then you measure the crater. So in other words, it might be 1 millimeter, 2 millimeters, and so on, and you compare that to a table, and it gives you some number. Probably a more common test in industry is something called the Rockwell test or Rockwell hardness, and it's kind of similar to the Brunel, but here instead of a tungsten ball, it uses a diamond tip. So that is again forced into the material, and then you measure the depth. So instead of measuring the diameter of a cone, you measure the depth of the penetration. Gives you the same kind of data, and what you'll end up with is something called a Rockwell hardness number. So some common values for steel, for example, might be 90 or 100 or something like that. And that concludes part 3. And I hope you learn a little bit of something about material testing.